What has happened to that drive? What is it that's really going to drive us to grow? What is it that's going to drive us to innovate? And that is again, like I said, one of our fundamental questions that we have to address. What I want to do is just bring your attention to a couple of the models that Porter had brought up. Earlier in the slides, I said, he found very little correlation between one variable and another, that sort of thing. And I know that some of you might have looked at these charts and probably didn't even really look at the charts because of the technical jargon that's down below here. But just to put some meat behind the words, I want to try to explain what's going on and very easily and very briefly explain what these technical terms really mean here. The equation, the R squared, the p-value, things like that. For this, let's take a look at the, let's see, this would be the compounded average growth rate. That's what CAGR stands for in the Porter article. Compounded average growth rate of average wage, and he looked over a 10-year period, 1990 to year 2000. And this is in various economic areas as identified by the Bureau of Economic Analysis. In a minute here, I'll show you what our economic area is, as identified by the BEA. And it's not up here, incidentally, but I'll identify it for you. If you look at the average wages, let's say in 1990, and we're looking at the growth rate, and what we're trying to do here, how many of you have actually taken, let's say, a statistics course where you were exposed to regression analysis? Okay, so then you know what this is. Okay, so all we're trying to do in this technique, and it's probably not the most appropriate modeling, by the way, ordinary least squares is what he used here. You could tell right away it was probably not the best. We're trying to fit a line into the data such that the line is set in such a way that the average differences between the actual observations as noted by these little dots in the scatter plot are at their minimum. The differences between this and the line are minimized, so we kind of fit the line here. And what this tells us is that, oh, there's an equation. All right, this equation tells us the relationship, let's say, between the compounded average growth rate of average wages over 10 years and the average wage in 1990. And what we're seeing is that this slope is not very high. The slope, look at this slope. It's in engineering notation, which tells us this is, let's see, this is 7 decimal places to the left of 0. And so the slope is not very high here. So according to his data, there is very little correlation between the CAGR of average wages, the compounded average growth rate, and the average wage. So the starting wage has very little to do with the growth rate of the wages would be. That's kind of his conclusion. Now, some of you might be looking at some of those technical things. I did this in my class for the Economic Development Certificate as well. Because they looked at the R squared and said, I don't know what that is. Anybody remember what the R squared is? You remember what that is? What is it?
Would you want the R squared value to be at least 60% or better?
Well, you would think. Okay, I was waiting for somebody to say that. Okay, you would think. Unfortunately, that's how we teach it to you. Okay, the R squared is not that.
Well, it's not all that important, but still, usually the better it is.
Well, yeah, and you see in this case it's 6%. Right. But we're still going to say it's statistically significant. Because to look at what this means, by the way, is that with a very low R squared, that means not a whole lot of this is explained by this line. The more of this that's explained by the line, the higher the R squared. For the one